Hi, folks. Today we're going to talk about graph theory. Graph theory is one of my favorites, and it's probably the most relevant to our day-to-day lives. And so let's see if we can do a good job of explaining this one. So to begin with, let's talk about Königsberg. And so in 1736, Leonhard Euler presented a problem which fundamentally changed our understanding of mathematics. Consider the map of Königsberg, Prussia, to the right. It is a city which has a pair of rivers meeting in a central island and 7 bridges. Is there a path which crosses each of the bridges exactly once? And so if you look at this, and you can pause the video and try, is it possible to find a starting location, cross all of the bridges exactly once? And if there is, where would you want to start and where would you end? This problem introduced the world to both topology and graph theory, and it really reshaped how we view mathematics. It created new fields, new large branches of mathematics. When we think about before this, you had algebra, you had analysis, which is basically calculus. We had geometry, we had discrete math, which is all about counting principles. This gave us topology, which is another major branch of mathematics, which allowed us to do all of the stuff we've done in physics for the last 100 years, as well as everything related to graph theory and networks and many, many, many applications. And so this is kind of a turning point. Let's see if we can understand how Euler did it, but let's also understand the structure of what's going on here. For now, let's start with our structures. And so what is graph theory? Graph theory is the study of graphs, but not the Cartesian graphs you may be used to. In this context, we think of a graph as a collection of points which are somehow connected to one another. The example to the right shows a graph with 6 points, A, B, C, D, E, F, and 8 connections. In this sense, graph theory is the study of organization, relationships, and connections. I usually think of topology as talking about how we can group things together, and graph theory is about how we can actually make connections between individual things. And when you think about how we determine how things are connected in the real world, well, there's a lot of ways we can connect things. Formal definitions. All right, so we have a simple graph. A simple graph G consists of 2 things. A set V, whose elements are called vertices. These are also called points or nodes. And the singular form of vertices is vertex. And so this is a vertex, this is a vertex. We have 6 vertices in this graph. A set E of unordered pairs of distinct vertices is called edges. These are the connections between the points. We can denote such a graph as G of VE, and so a collection of vertices and edges. But usually, instead of writing it in a set theory perspective, which, we love set theory, but instead of writing it in set theory notation, we will use a visual such as this to show all of the graphs and the edges, or sorry, all of the vertices and the edges. And so here is our simple graph. The set of vertices would be 1, 2, 3, 4, 5, 6. The set of edges written in a set theory notation would be 1 to 4, 2 to 4, 3 to 4, 4 to 5, and 5 to 6. And so this is the set notation for the graph. We will not use the set notation that often because we have a nice visual. About vertices. Vertices are the points on the graph. And so some graphs have vertices which are simply labeled with a number, a letter, or colors or variables. But they can also carry information such as values, labels, or even lengthy written out information. Whenever we are thinking about a cluster diagram where we are trying to get together information about a number of different individuals or events, we are usually saying that these nodes, these vertices, are carrying with them different information. The degree of a vertex is the number of edges which the vertex connects to. And so in this case, 0 is connected to 2 different edges, and so it has a degree of 2. 1, 3, 2, and 4 all have degree 3 because they each have 3 different edges connecting them. And then vertex 5 has degree 2 because it has 2 edges. Thinking edges, well, an edge connects 2 or more vertices. Much like vertices, edges can contain additional information. And so if there is a number associated with the edge, we would consider it a weighted graph. If each edge has a specified direction, we would say that it is a directed graph. In this case, this example is a graph which is both weighted and directed. We also have other variations of graphs. And so the simple graph was just having edges connected in a nice way, but a multigraph is a graph in which a pair of vertices are connected by more than one edge. And so if we look here, the red ones, well, we have 2 different edges connecting these points. We also have loops. And so a loop, which is done in blue over here, is something which connects a vertex to itself. A pseudograph is a multigraph that has loops. But realistically, in general, when we're talking about simple graphs, multigraphs, pseudographs, weighted graphs, directed graphs, we usually just call them graphs. And so a graph is a general term for any of these types of objects. So let's talk about how we can define equivalent graphs. And so much like when we were talking about topology, we had homotopy and homeomorphisms. Well, there's different ways of determining if graphs are equivalent as well. The first is isomorphisms. And so 2 graphs are said to be isomorphic if there is a one-to-one correspondence between the vertices and edges. Essentially, how the graphs are connected has to be exactly the same. The graphs themselves might look different, but the way that they are connected has to be the same. We treat isomorphic graphs as though they are the same. And so in this case, we have letters. Each of these letters has 5 vertices. And so there could be some which are isomorphic. And in fact, if you look, A and R, they're connected in the exact same way. And so we would say that they are isomorphic. The only difference is this one, the vertices are going in a straight line up and down instead of at an angle, and there's a curvy bit here. It's still just edges connecting these points, and they're all connecting in the exact same way as A. F and T are also isomorphic, and it might be harder to notice with that, but if we look, this vertex here in the center of the F is connected to 3 edges, while this one at the top of the T is connected to 3 edges. From there, we can see that if we flattened this one out, the bottom one on the F out, and then brought this curve or this vertex in the upper right up to the left diagonally, then we would get an upside down T. And so the F and the T graphs are the exact same graphs. Similarly, X and K have the same structure, and so they're isomorphic. And Z, M, V, and S are also all isomorphic to one another because they're just following a line, basically. And so we have this one to this one, to this one, to this one, to this one. V, M, S, and Z are all just following a straight line. So we had isomorphic graphs. We also have homeomorphic graphs. And so given a graph, we can obtain a new graph by dividing an edge of G with additional vertices. And so this is called a subdivision. And so if we wanted to, for example, with this upper left graph, if we wanted to, we could create a subdivision by putting a new vertice, a new node, right in the middle of that edge. We can also create a new graph by removing a degree 2 vertex. And so if we look at the center here of this upper left graph, well, this edge is degree 2. And so this vertex is degree 2. If we wanted to, we could remove it. And this would be a process called smoothing. We would create a new graph, but we're allowed to do that. And if we do, we get graphs which we consider homeomorphic. And so if two graphs can be made isomorphic to one another through a process of subdivisions, the graphs are called homeomorphic. And so through subdivisions and smoothing, if we can get one graph to be the other graph, then they are homeomorphic. This is actually the same homeomorphic definition that we had in topology. Topologically, being homeomorphic is the same as being homeomorphic in graphs. And so here's a practice problem. Consider the four graphs to the right. What is the degree of each node? And then which graphs are isomorphic and which ones are homeomorphic? If you'd like, pause the video and give it a shot. What's interesting about this one is when you look at them, it turns out all four of these graphs are the exact same graph. And so looking at them, the blue and orange dots are each connected to all of the other nodes. The green is only attached to the blue and the orange. The green is only attached to the blue and the orange. Same here, same here. And the, what did I call this? Dark blue or dark purple. The dark purple is connected to the blue and the orange only. And note that's the same in all of these. All four of these graphs are isomorphic to one another. And so therefore they are trivially homeomorphic too. We didn't even have to do any subdivisions. They are all the exact same graph, just presented in different ways. Here's a practice problem. Consider the three graphs to the right. Are they isomorphic or are they homeomorphic or neither? Which ones match and which ones don't? If you'd like, pause the video and give it a shot. And so taking a quick look at it, one thing we can do is we can consider the number of nodes which we have, the number of vertices. And notice that A and C both have 6 vertices, whereas B does not. Because of that, we know that B is not going to be isomorphic to either A or C, but there is a chance that A and C do have the same structure. What we'd really want to do is we'd want to figure out how many edges each one is connected to and see if the structure matches up. And it turns out they don't. When we look at this, we have a 2, a 2, and a 2. We have 3 2s. For this one, we also have 3 2s. But when we look at the structure of it, this C1 has 2 of the 2s right next to one another. And so each of these is connected to 2 edges. Whereas for this one's connected to a 4 and a 3. This one's connected to a 4 and a 3. And this one's connected to a 4 and a 3. The structure of A and C is different. And so they're not isomorphic. None of these are isomorphic to one another. They are, however, all homeomorphic to one another. And if you want, you can kind of look at B and see how you can get B to turn into both A and C. And so looking at A, if we just brought this bottom left edge in and brought this one to the center, we could then remove the center node using the smoothing technique, or we could just do a subdivision here in the center. And we would get that A and B are the exact same thing. Similar here, if we look at graph C, well, if we brought these two nodes together, just eliminated one by using smoothing, or if we did a subdivision up here on the top, then we would get that B and C are the exact same graph. And so none of these are isomorphic, but they're all homeomorphic to one another. The next big topic is paths. And so given a graph, a path is a sequence which goes from vertex to vertex by following the edges. Depending on who you're talking to, though, these may be called walks or they may be called simple paths. For our purposes, we're just going to call them paths and be done with it. And so to write out a path, in set theory notation, you would list out the alternating sequence of vertices and edges. And so you would say, we start at this vertex, then we hit this edge, then this vertex, then this edge, then this vertex, then this edge, then this vertex, then this edge, then this vertex. It can be very tedious to write this all out in set notation, but it is possible. I mean, set theory is the foundation of most of the math we do. The length of a path is the number of edges along the path. And so we have a number of different types of paths. We have a simple path, which is a path which doesn't repeat vertices or edges. And so if we just go 1, 2, 5, 3, 4, that would be a simple path because we're just following this outside bit. We're not repeating any vertices. We're not repeating any edges. A trail is a path which doesn't repeat edges, but can repeat vertices. And so if we go 1, 3, 4, 1, 2, we repeated 1, but that's okay. In a trail, we can repeat vertices. We just can't repeat the same edge. And so we can't go 1 to 3 to 1 to 3. We'd be repeating this particular edge too many times. A path is closed if it begins and ends at the same point. So if we do 1, 2, 5, 3, 4, 1, that is closed because it began and ended at 1. A cycle is a closed trail which includes at least 3 vertices. And so 1, 3, 4, 1, that's a cycle. 1, 2, 5, 3, 4, 1, that is a cycle. A tree is a simple graph which has no cycles. And so this is not a tree because it has multiple cycles. Let's now talk about directed graphs. And so in a directed graph, each edge has a direction. Essentially, it's a bunch of one-way streets. You could have two-way streets where you might have something coming or an arrow coming back in the same direction. But yeah, in set theory notation, edges of directed graphs are represented by ordered pairs, with the first value your start and the second value your edge. Yeah, your second value your edge. No, where you start and where you end. And so in the graph to the right, a path could be written as A, then AB, because this edge is connecting AB, then B, then BE, then E, then ED, then D, then DG, then G, then GH, then H. Again, there's a reason why we don't often write these things out in set theory, because the visual gives us a clear understanding of what we're doing, and we could just trace that path instead of writing it all out in set notation. If a path is constructed which involves an edge going the wrong way, we call that a semi-path. Let's talk about connectivity. So a graph is connected if there's a path between any two of its vertices. Otherwise, we would say it is disconnected. And so directed graphs have 3 types of connectivity. We have strongly connected. That means for any vertex U and V, there's a path from U to V and a path from V to U. And so if we have a graph and we can go back and forth between any 2 points, it's strongly connected. Unilaterally connected means for any vertices U and V, there's a path one way or the other. Maybe not both, but there's a path from one thing to the other thing. We then have weakly connected. So weakly connected means for any vertices U and V, there is a semi-path connecting them. When we look at this directed graph up here, if we wanted to go from A to any value, we could do that. Let's see. If we wanted to go from F to G, we might have a hard time. And so F can go to H, but F cannot get back to G. And so in this case, we would say that this graph is not unilaterally, it is weakly connected. There are semi-paths which are connecting them, but there's no way to get from F to G or to get from G to F. And that's connectivity. If it's just a normal graph, we just say connected or disconnected, and we don't have to worry about any of those other terms. Hey, we just did this one. And so reachable. A vertex V is reachable from vertex U if there is a path from U to V. And so consider the example to the right. Which vertices are reachable from vertex A? And then which vertices are reachable from vertex C? And which vertices only reachable to H? Which vertices are only reachable to H? Well, in this case, A is reachable, or A can reach out to any of these other things. And so all of the vertices are reachable from A. A can go to B, A can go to C, A can go to D, A can go to E, A can go to F, G, and H. Which vertices are reachable from vertex C? Well, C, it can't go to A or B, but it can go to any of the other vertices. And which vertices are only reachable to H? Well, in this case, E can go to H, F can go to H, and G can go to H. All of the others, they have other options. Well, actually, E is not only reachable to H, because E could reach out to other things as well. Keep finding typos. A path is an Eulerian path if it has these two characteristics. And so it begins and ends at the same location, and it goes through every edge exactly once. Well, now we're starting to get back to that idea of the Konigsberg problem, which we started with. And so for it to be Eulerian, it's okay for an Eulerian path to repeat vertices, but you're not allowed to repeat edges. We say that a graph is semi-Eulerian if it goes through every edge exactly once, but it doesn't necessarily have to start and end at the same location. And so Eulerian path, you begin and end at the same point and go through every edge. To be Hamiltonian, well, a path is Hamiltonian if it begins and ends at the same location and it goes through every vertex exactly once without repeating edges. You do not have to go through all of the edges, but you have to have a path which goes through every single vertex without repeating any edges. And so a graph with a Eulerian path is called an Eulerian graph, and a graph with a Hamiltonian path is called a Hamiltonian graph. Let's look at some examples. And so if you'd like to try on your own, here are 4 graphs. Which ones are Eulerian and which ones are Hamiltonian? So remember, Eulerian means it's a path which goes through all of the edges and returns to your starting point. And Hamiltonian, it means that it's a path which goes through all of the vertices and returns to your starting point. It doesn't have to go through all the edges. And here's our solution. And so in this case, the top 2 are Eulerian because we can have a path which goes through all of the edges and returns to your starting point. Here we could start at the center point, make the triangle, and then make the bottom triangle, and we are back to our starting point. The bottom are not Eulerian. It turns out no matter where you start, you cannot create a path which goes through all of the edges and returns to your starting point. As for Hamiltonian, well, these on the left are Hamiltonian. We can go through all 4 points and start and get back to your starting point. Same with the bottom one. If you just go around the diamond there, you have gone through all 4 points and returned to your starting. We don't have to go through all of the edges to be Hamiltonian. These 2 are not Hamiltonian. And so when we look at this, if we start at the central point and we try and go up and make the triangle, well, we're back to our starting point already, and we can't repeat points. We can't repeat vertices for a Hamiltonian graph. Same with the bottom one. This is not Hamiltonian because we can't go through all 5 of these points and return to our starting point. And so not Hamiltonian. So let's go back to Königsberg. With all these tools, we now have a way to think about this. So consider the map of Königsberg, Prussia to the right. Is it possible to create a path which crosses all of the bridges exactly once? And if so, where would you have to start and where would you end? We're asking the question of whether or not this is a semi-Eulerian graph. And we're using the tools of topology and graph theory to do this. And so what Euler realized is that the size of the islands does not matter. Each island could be treated as a point. In topology, we call this homotopy, the idea that we can demorph each of these regions into a single point. Euler also developed the idea of edges as a way to represent the bridges. And so we can tell that this graph is obviously Hamiltonian, but is it Eulerian? Is it semi-Eulerian, or is it neither? And that's the big question. If you'd like, give it a shot. See if you can determine it. Final thoughts. The fundamentals of graph theory give us a new structure with which to analyze the world around us. When you start to look around, you'll quickly realize that graph theory comes up whenever we consider organization, relationships, or connections. Every flow chart, every strategic plan, every seeding chart, every travel map, every family tree, every desktop layout, every garden, every biological and physical process, it's all graph theory. Where do you see graph theory in your daily life? Well, this example to the right, this is artificial intelligence. If you're doing neural networks, this is how artificial intelligence actually works. It's just doing a little bit of linear algebra on a graph. And we have our inputs, we have our outputs. And the question is, how do we get from these input layers to this output layer? And yeah, whenever we think of any form of connection, any form of relationship, if we are asking how trees are connected to their leaves, I'm using trees a lot because I see a tree out our window. If you are talking about a family tree, if you're talking about organizations, if you're talking about anything, I mean, anything where we are connecting ideas, we can use a graph to visualize it. With that, I'll let you get to work exploring where you find graphs in the real world. Good luck, folks.